Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So we continue our lecture with 4.3, which is on how to convert governing equations to algebraic equations in order to do these numerical simulations. So in this chapter, basically we are going to discuss the basic derivations of the FDM, which is the finite difference method, and FVM, finite volume methods. Next, we are going to consider an appropriate applications of these discretization techniques to solve governing partial differential equations numerically. So in this chapter, we are going to discuss one of these cases where we are going to discuss the first one, the pure diffusion in steady state. Meanwhile, for the rest, you can try to study by your own because see, this topic is quite long, this example. So I'm afraid that we're not going to have enough time to cover all of them in the lecture. Okay, as you know that this is actually equations for the pure diffusions in a steady state and in one dimensional. As you can see that it has only x component is x directions, which is one dimensional, where this is the diffusion coefficients, which is this depends on the properties phi. Okay, if you look for u, okay, there is it has its own transport coefficients. Okay, a diffusion coefficients. If it's t, for example, it has different. So you need to refer back to the table that we discussed in chapter 3 before. Okay, how we get this pure diffusions equation? Actually, it comes from the full transport equations. This is a result of we have a steady, and so this is all our advections terms. Advections. And these all are the diffusion. So this is only pure diffusion, so we only have the right terms. And since it's only in one dimensional in x direction, so you can eliminate the other two dimensions. So we only have these terms and also the source terms. And so that's how we get these equations. This is pure diffusions in one dimensional steady flow. Okay. We are going to compare the discretizations using finite difference method and finite volume method. Okay, first we go into this finite difference method first. So the first step in developing a numerical solutions involve dividing the geometric domain into several nodal points. So in this case, since it's only one dimensional, where we use P as our point of interest, and is surrounded by west and east. So this is like one dimensional. If there's two dimensional, we have another two, which is north and south. The diffusion term that we seen before actually can be expanded into this, and from the expansion, there are two first order terms on the left, and we also have a second order. And so by using the equations for the first and second order derivative, which is we discussed in the finite difference method in slide 6 and slide 7 before respectively, so the equation above can be written as these equations. So basically what we have here, comes from the first order terms on the left where we have this, and comes from the second first order, and this is from the second order. These all are the discretized first and second order terms for finite difference method. So you can just substitute this into using the equations derived in slide 6 and slide 7. Okay, the equations just now, it can be rearranged in this way, where we can try to factorize all the coefficients of each of the properties. So we separate all the properties by phi p of that point that we are looking for, focus on, and the phi in east and west. So we arrange it this way, so that and we try to put in into this simple equations form, where phi we go to phi, and so whatever that the factor or the coefficient of that properties is actually equals to this coefficients a, p, a, e, a, w, and the one that's without the phi we put it as b. So usually this is where the source terms belongs to. So what we get is the AE is equals to this one. This is your AE. And for AW is this. And AP is this. And usually AP is equals to AE plus AW. So if you add together, AP is equals to AE plus AW. So if you add these two terms, basically you get back this 2 gamma p squared, because these terms will cancel each other. So usually this is the relationship between the AP, AE and AW. So the rest will be as a source term will belong to B. Okay, there is a finite difference method. So here we will discuss on the discretizations of the governing equation term by using the finite volume method. So instead of using nodes like in finite difference method, here we have a control volumes that is surrounding P. So by using the equations for the discretized first order derivative in page 9, you can go back and refer to this. We can discretize it into these terms, where A here is the projected areas on the west and east of P. So here we have P, so this is west and east. So there's an area that is facing west, and this is the area that is facing east. So usually for manual calculation, we can just assume that the size of the projected areas to be the same. So because if we do it in simulation, it will be like no problem if the area is different. But for us to do it manually, usually we just take this area as unity or equals to 1. However, the sign for these two opposite surfaces need to be in the opposite directions. It is like one is where the properties comes in, one is the where properties goes out. So you just want to make sure that the properties is conserved. So in this case, we take that the one on the west is negative, so AE is supposed to be positive in order to make sure that the property is conserved. If it goes in, it must goes out somewhere. Since this is only one dimensional, it has only one entrance and one exit. So one of them must be positive, one of them must be the opposite sign. So the remaining terms other than these terms can be written as the source term. So as you remember, these two here indicates this is only one dimensional, because we have only two lines, left and right. So we take this into these equations into this. So basically what we get, this is the final form of the discretized equations. And for this we know that del over del x del phi over del x equal to 0. So this is the governing equations, and this is the discretized equations. So by assuming the linear gradient profiles for these points between W, P and E, so we can approximate that the gradient here is linear. So instead of using this, we can change it into this. a linear gradient. So we substitute this into these approximations, and then we substitute back, and this is what we will get. So we arrange this, substitute the one that we derive from the linear assumptions into the first equations at the top. So basically we will get this. And then once we obtain this final form of the discretized equations, we can rearrange it again like the one that we did in the FDM. So we expand and we factorize. So here we have phi p, phi e, and phi w, and the one that is without phi, without the properties. So from here we can assign which one is A, E, A, P, and A, W. So from here we can say that this is the AP, this is the AE, and this is the AW, and the rest is B. So this is what we obtain for this. If we use finite volume method, this is our coefficient. So we compare between the FDM and FVM discretizations. So from what we obtained before this, the top one, this is the coefficient from FDM, and this is the coefficient that we obtained from the FVM. So they look different, but if we consider a special case where the diffusion coefficient is specially invariant, which means that these diffusion properties at east and west, they are the same, because this is when if we assume that the mesh is uniformly distributed. Okay, so all the properties that comes in equals to the property that goes out. So we just simplify it that way so that it will be easier for us to do it manually. If it is not arranged uniformly, it's going to be very difficult to solve manually. So by doing so, and if we take the mesh uniformly distributed, this delta V is basically equals to del x power of 3, and this is equals to del x, and this is equals to del x squared. So basically they can be simplified or eliminated. So basically what you will get like del x power of 2. So it can be simplified. So same goes to the one at the top. So if it's like the diffusion coefficient is the same for east and west, and for P as well, so this will be cancelled out, and this will be cancelled out, because these two has the same value, these two has the same value as well. So you just substitute this with the same value. Basically for this kind of case, the diffusion coefficient is only one value. So both of them will get the same result. So for this case, this kind of case, FDM and FVM give the same results. Here we take an example in discretizing the governing equations. So consider the problem of steady heat conduction in a large brick plate with uniform heat generations. So we have two phases A and B, as shown in this figure below, are maintained at constant temperature. The governing equation is of the regenerate form presented in equation 4.15. So the diffusion coefficient here, actually this is the governing equation. Actually, this equation 4.15 according to the book, but I don't think that actually this is representing the governing equations. So yeah, perhaps there is some error in the book. Okay, so I'm not sure actually which equation it's referring to for governing equations for this temperature, but I believe that this is belong to the energy equations. So we have the diffusion coefficient gamma governing the heat conduction problem becomes the thermal conductivity K of the materials. So it says that okay, gamma here is K. So for a given thickness L equals to 2 with constant thermal conductivity K equals to 5 watt meter squared per Kelvin, determine the steady state distribution in the plate. So temperature at TA and TB are respectively 100 degrees Celsius and 400 degrees Celsius, and the heat regeneration Q here is 500 kilowatt per meter cubic. basically the question gave us the boundary conditions and also the source term as well. So we have this A, this is the boundary conditions you have. And for this we use the finite volumetization where we have the TA and TB. Okay, for this case, we distribute them into 4 points, 4 nodes. Okay, 1, 2, 3, and 4, where they are equally spaced, but except from 1 to TA, the space is only half. And same goes to from point 4 to the TB, the gap is half the compared to the rest, del x over 2. Okay, so first we try to solve for node 2 and node 3 first. Okay, as usual, you need to find the equations for this discretized equations. So our main things we need to find is, okay, as usual, this is actually comes from AP phi P equals to A is phi is plus AW phi W plus B. Okay, so here we know that the properties that we are trying to measure or calculate is temperature. Phi here is temperature. So okay, you can substitute it into temperature straight away. And then we need to find our AE, AW, and AP. Okay, so we can just use the one that is already derived from the previous subchapter, wherefore with pure diffusion, because this is a pure diffusion, because it is a steady state and only one dimensional, and there is no velocity involved, so no advections. So this only like fully diffusions. You can use that equation straight away. So before this, we already obtained these terms, all these terms, and where we found that AP equals to AE plus AW. So you can just substitute straight away. Actually, these things relies on the governing equations, which I'm not sure what actually the governing equations looks like, but perhaps you can like try to look at this for thermal conductivity, and you can try to compare and try to derive it and discretize it, and perhaps you can get the reason why see the diffusion term is Ka. Okay, because in the problem it's mentioned that the diffusion coefficient is equals to K, becomes the thermal conductivity, but somehow here they write it this equals to Ka, but eventually this A is equals to unity, so it doesn't really affect the final result. So from what my understanding is, this is supposed to be equals to K if we refer to the problems, but however these things, this depends, relies on the governing equations. So yep, just substitute this, you can get here, and AP equals, and they are the same, and the source term. So here we have the source of the difference between this A, between these 2 points is Q, is the heat generations, which is that is the source term. Okay, for constant thermal conductivity and uniform heat generations, the equations becomes this. So as usual, because the temperature is increasing from east to west, so we can expect that the total energy at west is more than the one at east. So basically, these terms plus this, you will get these terms. Basically, that's the idea. So you can change this into by using linear approximations. This is the gradient between 2 points. So we just take this difference between 2 points divided by the gap. So this is for point at E. So as we know that from this point to the second point, the gap here is del x. So that is how these equations comes from. Okay, meanwhile, if you want to compare to A, since actually this is half the distance compared to the one before, to the east, this is the equation, this is the distance, actually delta x over 2. And it's like this is the source term, which is from here. Okay, once again, suddenly this A appears. So I'm not really sure why. So this perhaps you this is something that you can ponder on. And if you know what's the reason, I really appreciate if you can share it with me. Okay, then what we need to do is we need to factorize it and try to reduce it into this form. Okay, if we try to expand it, what we are going to get is we're going to get something like Ka Te over del x minus Ka Tp over del x minus Ka Tp over del x over 2 and plus Ka Ta del x over 2 plus Q del x equal to zeros. Okay, so by factorizing P, E, and W, okay, and what you can get is this will give you the E. So AE is equals to Ka over del x. Okay, meanwhile for W there is no TW here, so that's why we have AW equals to zeros. And meanwhile for the TP, you can get the AP from here. So by doing this, basically you can get that AP is equals to minus Ka over del x minus 2 Ka over del x. So basically this is equal to AP. Oh sorry, this is equals to AE. And here AW is equal to zeros plus AW, and then we have this is actually plus because we move it to the right. Okay, here what I written here is everything's to add on the left hand side. So when we want to change into this, we put it on the right. Okay, so we just change it into plus actually. So what we get is 2 Ka over del x. So that's how we get these terms, and the rest is the source term. This is the source term, so this goes into here. So these all are for the A, E, AW, and AP for node 1. Okay, for node 4, we just going to do the same thing. So this is actually for node 1. So for the node 4, the idea is the same. This is del x over 2, and this is del x, and just do the same thing like this. But this one, this is the one that have the TB minus TP and the del x over 2, and this is the full length to the west. So basically for this case, this is P, and this is somewhere after TB, and this is your west. So just do the same thing. You get almost the same results, except for this one. The one on the east is zeros, the one on the west has value, and this will give you the same result as well, and this will give you something like this B, and in the TB before this we have TA. Then all of these results we can and then we can just substitute the value is given, which is K equals to 5 and Q equals to this, and del x equals 0.005 and area equals to 1. And by substituting all that 4 equations, this is what you get. This is usually the one that obtained from node 1, and this from node 2, this from node 3, and this from node 4, the one that we just derived before this. So it can be written like this as well. Like this is list down for node 1, 2, and 3, and 4. What is all the coefficients AE, AW, AP, and B for each of these nodes? Or you can also write it down in terms of matrix. So what does it mean by here is basically it's the same thing as this. So 300 T1 minus 1000 T2 equals to equals to 2000 TA plus 2500. Okay, actually from this, you can also already find what are the values for temperature at each of the nodes at node 1, node 2, node 3, node 4, because TA and TB are already given. They are your boundary conditions, which is this is the 100 degrees Celsius and this is 400 degrees Celsius. So basically this actually what all your simulations does actually in the mesh. Like for example, in the mesh we have like this, and we have a lot of nodes. Okay, so we have a boundary conditions. Like for example, we have like temperature equals to 100 here, and then we have temperature equals to 400 here. And then what the simulation does actually, it calculates the value at each of these nodes by using this. And this is only for temperature. But so for like, if you have a momentum equations, if you have advections, it will do the same thing for all your like U, V, and W. So that's why boundary conditions is very important. So boundary conditions are the one actually can help you to simplify or reduce the number of unknowns in your equations. Like for this example, you have like 6 unknowns. Right? You have 6 temperatures, T1, T2, T3, T4, TA, and TB, but you only have 4 equations. So by having a boundary conditions, you can reduce the number of unknowns. And by doing that, you can do like all these like elimination or substitutions method to solve the unknowns. So yeah, that's for this lecture. Thank you.